Okay, now we did all that, so let's solve an equation, solve a problem. So what we have here is a cantilever beam, and you can see there's two distributed loads. Both of them are uniform. What we want to have is an equation for the shear force V and the bending moment M for any location of the beam. And we'll start our origin right here at point A. That's important for these problems. Then we want to plot this for these beams using our derived functions. Okay, now I'm not going to make you do this on your own. We're going to do it together, though it's really just a little bit of integration here. It's still not necessarily fun. Okay, so first make a free body diagram. Now once we've done that, we can begin to solve everything. So from this we only have to use two equations. So sum of the forces in the y direction. We're going to have a distributed load right here and a distributed load right here. Their magnitude is going to be equal to their magnitude of the load times its length. Do that for both of them and I add them together. Then Cy is going to be resisting that. So Cy is going to be equal to the sum of those loads, which makes sense. Okay, how about the moment? Well, the moment's going to be equal to, moment at C, plus the force caused by this distributed load times the distance to it, which will be B plus A over 2, plus the force from this distributed load times the distance to it, which will simply be B over 2, which is what we see here and here. And then we solve and we get our moment C. I don't make you do many just analytical problems, if any. I prefer numbers, but it's good to see how you're doing this, and you may have to take the actual steps. Okay, now that we've done that, we've got to start determining our shear force and bending moment at the points where we care about them. So let's do section AA. This is just cutting into a point that is inside of that first distributed load. And so we're going to go all the way till the end of that first distributed load. We're going to include all of it for this section. Now when we do that, we have two equilibrium equations. Okay, so the sum of the force in the y direction is going to be simply this distributed load minus my shear force. So my shear force is going to be negative. It should be pointing up instead of down. And I'll do a very similar thing to get the moment. So for this section, I can see that as my distance x increases, my shear force is increasing, or I guess in this case decreasing. It's getting more negative. And as my distance x increases, my moment is also getting more negative. Okay, we did it for one section, and so as you might be able to guess, we now have to do it for the second section. So look here how we're defining this distance right here. Obviously we've already gotten a distance A. We went from 0 to A, and now we're in the second section. We can't just say, well, this is now 0. No, our origin has to be the same both times. And so with that in mind, we say, okay, well, this whole distance is x. Yes, we're starting from here, it's the 0. But we'll make it a little bit easier on ourselves and say, well, we're only going to do things that are from A to B. So this will be x minus A. Okay, so we do that. We have our distance, A right here. We already knew that. We have our second load right here, and we're putting in terms of x minus A because it's going to change. If we can get that our shear force in this section is going to be equal to the magnitude of that initial load. So we're starting there, and then we're going to be slowly decreasing more. And our moment is also very, very similar. And what do we get here? Well, we see that, surprise, surprise, the further we get away from that point, it's still going to be affecting it. That original load, it doesn't just stay constant. It's going to be having an increasing effect because it's going to be further and further away from the point where I'm applying this. And that load right here from B is also going to be causing us issues. Okay, now with that in mind, we have an equation for this first section. Check. We have an equation for this second section. Check. And if we want to, we can now plot both of those. And they would look something like this. So what do we see here? Well, we see that we have a linearly decreasing shear force because we have a constant load here. And this is the slope. Slope is constant. As we get to the second section, we have a smaller magnitude. At least it's visually smaller, though technically we can change the numbers and make it bigger. And so we have a smaller slope, but it's still negative. And then right there at the end, we jump back up. That's important. That point load right there, that support load, jumps us back to 0. You always start at 0, and you end at 0. Okay, start at 0, end at 0. What you can also figure out possibly is that this is going to be the slope. The magnitude of this line at every single point is the slope of this one. So since it's getting more and more negative, this is getting a higher and higher slope. And of course, that continues as we go down here. Other things you can think of is the order of these functions. This is a 0th order because it's constant. This is a first order function because it's a linear line. This is a second order because it's now a polynomial. And so they're going to increase in order as you go down. So that's it for this problem. Thank you for listening. I hope it helps you. And I'll see you all later. Have a wonderful day. Bye-bye.